The ideal gas law. So we've discussed 3 different relationships involving pressure, volume, temperature, and number of moles of gas. And we can put them all together. I'm guessing that most of you are not interested in the derivation of the ideal gas law from those other gas laws. So I won't go into great details. Volume is proportional to 1 over P, and volume is proportional to T. So that means that volume is proportional to T over P. Volume is proportional to N, so volume is proportional to N times T over P. And if we rearrange that and put a constant in there, then we have an equality. So the volume equals nRT over P, and the rearrangement we get is PV equals nRT. PV equals nRT. This is the ideal gas law, known affectionately as PIVNERT. And R is a constant. It's called the ideal gas constant. It can be expressed in different units. If you use different units, it's going to have a different number, but the one we use the most often is in terms of liters, atmospheres, moles, and Kelvin. So then R is 0.08206 liters times atmospheres per mole Kelvin. The weird units are because these units need to cancel with the pressure, volume, number of mole, and temperature units. So they just left them all and they cancel out. And these units here tell us what units we need in our pressure, volume, number of moles, and temperature in order for things to work out. So we use atmosphere for pressure and liters for volume.
Do you know how they came up with that constant number?
Lots and lots of measurements. You measure a certain number of moles of gas, and you measure the pressure and the volume and the temperature, and you can calculate the constant. And you do that many, 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 many times, and average them and everything, and you come up with the ideal gas constant. Good question. So this is like the real deal. This is the ultimate gas law. From this, we can get all the others. And so I want to show you how you can do that. Because we could remember PV equals nRT, right? Just the one gas law. If you could just memorize the one, then you can get any of the others that you need from that. So PV equals nRT. If I divide, I'll give these subscripts of 1. R doesn't get a subscript because it's always the same number. If I divide this by P2V2 over N2RT2, P2V2 equals N2RT2, right? This is just PIVNERT, PV equals nRT, different set of conditions, right? So these are equal. As long as I divide by things that are equal, I'm doing the same thing to both sides, and this equation is still equal. Is everybody okay with that? So what I did is I took PIVNERT and I divided it by PIVNERT with a different subscript. Now the R's are going to cancel out. So say we have a situation where we have constant number of moles and constant temperature. Well, if the number of moles aren't changing, then N1 is going to be equal to N2, and they'll cancel out, right? And if the temperature doesn't change, then T1 and T2 cancel out. What does the right side of this equation equal? 1, right? So if P1V1 over P2V2 equals 1, then P1V1 must equal P2V2. Right? Whose law is that? Boyle's law. You can get all the other gas laws by doing this. There's also one called the combined gas law that your book never specifically talks about. And that's where you've got pressure, volume, and temperature changing. But you don't really need to memorize all those equations. As long as you can do this, you can get whatever you need. Okay, so I'll show that to you as we do. I'm pretty sure there's an example coming up. Any questions about this idea? That is a little bit cool, isn't it? You can figure them all out from PV equals nRT. Why don't we teach you that one first? I don't know. The books always do it the other way. So, yeah. And they never actually come out and show you that. So that's my little extra thing I'm telling you about. So let's do an example. A steel tank has a volume of 438 liters and is filled with 0.885 kilograms of oxygen. Calculate the pressure of oxygen, not oxygens, oxygen at 21 degrees Celsius. So let's pretend that we're clueless and we're looking at this and going, I don't know what to do, right? Make a table. The table works for everything. That's how I'm feeling right now. It's like, oh my goodness, it's getting late. I'm tired. So this is what we were doing. We're making a table. Let's put the numbers in. The first number is 438 liters. Liters measures, pay attention, liter measures volume, right? It actually says volume of. So that's the volume column. 0.885 kilograms. We don't like that. Let's skip that one. 21 degrees Celsius. What do we need to do to that? Convert to Kelvin. So that's going to be 294.15 Kelvin. And then we've got one more number. Well, I guess we're going to be forced to put that in here now. Oh, this was T, right? That's a temperature. Kilograms. Well, that's not a pressure. It must be N. It's related to N, isn't it? N is number of moles, but that's not the right unit, is it? It's kilograms. Can we find the number of moles? Sure we can. We learned how to do that. Okay, so let's do it. 0.885 kilograms of oxygen. How do we convert to moles? Molar mass, that's moles per gram, right? So moles of oxygen to 32, because it's O2, grams of oxygen, but that was kilograms. So we need to throw in a conversion for kilograms. We want kilograms on the bottom, grams on the top. Kilo means 10 to the 3, so we'll put it up here. And so we have 0.885 divided by 32 times 1,000. $27. This should have 3 sig figs, but I'm not going to round yet. 656 moles. Okay, so that's what we want to put in here. And we made the table, because that's what I told you to do. But what's funny about this table? There's no second row. And what are we trying to find? The pressure. Because this sort of thing happens on an exam, right? You knew how to do all of this stuff, and then you look at the exam, and your brain leaves the building, and you're like, I don't know what to do. Well, you don't panic. You just pick things apart, you write down what you do know, and you think about it. Okay, so there's no second row. So this is not one of those simple gas laws where we just have 2 units or 2 quantities, Boyle, Avogadro, or Charles. We don't have anything changing here. What equation do we know that has all of the variables in it? PV equals nRT. PV equals nRT. We're trying to find the pressure. We have N, T, and V, and R is something that we need to memorize. So I'm going to get rid of this little unneeded thing here. R is always the same, 0.08206 liters times atmospheres divided by moles times Kelvin. And yes, that's tedious. So we're going to take piv nert, which blessedly has no fractions, and we're going to rearrange it for pressure by dividing by volume. So we see that the pressure, which we're trying to find, is equal to nRT over V. Now you should look at your volume and see, is it in liters? Does it agree with this? Yeah, that's good. Kelvins, okay. Moles, okay. So let's go ahead and put everything together. If you don't check it before, definitely check it during so that you can make any unit conversions that you need. Moles, 0.0. Oh, stop with the yawning. You're making me sleepy. Liters, atmospheres per mole. Kelvin times Kelvin 294.15. Where's the uncertainty in that temperature? In the 4, the ones place. So that has 3 significant figures. And trying to get this small enough that I can draw a line all the way across, and that's all divided by 438 liters. The units then, moles cancel, liters cancels, kelvins cancel. So we get 27.656 times 0.08206 times 294.15 divided by 438. And that equals, this should now have 3 sig figs, right? 1.5, don't rotate on me, 5.2, and what's the unit? ATM, atmospheres. Okay?